Alright, so this is the second part of the same example, and we're going to complete the partial fractional decomposition now, and then finally come back and solve the initial value problem. Alright, so what we need to do next is multiply both sides by the least common denominator, which is s times s plus 1 times s plus 2. And we're going to do that by multiplying each term on each side by s times s plus 1 times s plus 2. That's one way to approach this. Or we could add the fractions together and then eliminate the denominators. Now what happens is the entire denominator goes away on the left hand side. For the first term, the factor of s cancels. For the second term, the s plus 2 factor cancels. For the third term, the s plus 1 factor cancels. That leaves us with just the numerator on this side, s squared plus 2s plus 8. On the left side, we get a times s plus 1 times s plus 2 plus b times s plus 1 plus c times s plus 2. Okay, and then the approach I'm going to take is by multiplying everything out and equating coefficients. I just want to mention that you can find a, b, and c for a linear decomposition like this, where you have linear factors, by plugging in expressions that make the coefficients of a, b, or c 0. So for instance, if we put in -1, a and b, the coefficients of a and b would be 0 over here. And therefore you'd be able to solve for c. By plugging in s equals 0, you could, the second two terms on the right would be 0, you could find a. Again, I'm not going to take that approach, but it is something you can do. Alright, so multiplying out on the right side, we get a times, multiplying out that binomial, we get s squared plus, combining like terms, we're going to have 2s and 3s, which is going to give us 3s plus 2. Distributing the s through, it's going to be b times s squared plus s. And multiplying the c through, we're going to get or the s through, pardon me, it'll be s squared times 2s. Alright, now next we're going to distribute the coefficients through everywhere and keep rewriting this. So we get here a s squared, well, alright, I'll just go ahead and do that. A s squared plus 3as plus 2a plus b s squared plus b times s plus c s squared plus 2cs. Okay, now we want to combine like terms. So we have these s squared terms. How many s terms do we have? 3 of those. And then there's just one constant term. Alright, so rewriting that now, we've got s squared plus 2s plus 8 is equal to, we want to think about the right hand side as some number times s squared. We're looking for these numbers a, b, and c, plus some number times s plus our constant term. Now what are the coefficients of s squared? Well, it's a plus b plus c. If we factor out the s squared, the coefficient of s would be 3a plus b plus 2c, and the constant term is 2a. And it's my preference to take this approach. I mean, I'm okay with either one, but just you got to know that for irreducible quadratic factors, you can't plug in numbers to make anything cancel out. Now, the only way this is possible is if the coefficient, right, the only way the partial fractional breakdown is possible is if this statement is therefore true for all s's, or as many s's as possible, and that's only going to be true is if the polynomial we have on the left is equal to the polynomial we have on the right, which means the coefficient of s squared must be the same on the left as it is on the right. The coefficient of s must be the same on the left and the right, and the coefficient of the constant coefficient must be on the left, must equal the constant coefficient on the right. That's going to give us a system of 3 equations and 3 unknowns. So 1 is going to equal a plus b plus c. 2, coefficient of s on the left, is going to equal the coefficient of s on the right, which is 3a plus b plus c. And lastly, the constant coefficient on the left equals the constant coefficient on the right. And then it's a matter of just solving that system. Now, luckily, this third equation is very easy to solve. We divide by 2, and we get a is equal 4. Then substituting in to the first equation and the second equation, we get a simplified system of 2 equations, 2 unknowns, 4 plus 1 equals 4 plus b plus c. And then 2 would equal putting in a equals 4. 3 times 4 is 12 plus b plus c. Okay, and then we would just solve for b and c, and you're used to doing that in some of our previous work. So I'm just going to tell you what those are and skip that work. It turns out you're going to end up getting b is equal 4 and c is equal -7, as you can check. So if you want to check that, pause the video and work that out. Okay, now keeping in mind what we had, we were writing this, if I go back a ways here, we were trying to rewrite this expression for the Laplace transform of y as a over s plus b over s plus 2 plus c over s plus 1, and now we figured out what those are, right, what those numbers are. So we took the Laplace transform of our differential equation and then isolated the Laplace transform, which we're writing as capital Y. That gave us s squared plus 2s plus 8 over s times s squared times s plus 2, pardon me, after in the factored form, times s plus 1. What we've just shown is that can equal a over s. Well, we come up with 4 for s, plus b over s plus 2, plus c over s plus 1, and we came up with 4 and -7 here. Alright, now I'm just going to rewrite that briefly, and then we're going to finish the problem. So we've got, I want to move the 4 off in front and rewrite that as 4 times 1 over s. I want to move the 4 off in front and rewrite that as 4 times 1 over. Now, keeping in mind that our goal is going to be to take the inverse transform, or say what these are related to via the Laplace transform, it's going to be nice to write that as s, instead of plus 2, s minus -1. For the last term, move the -7 off and rewrite that as 1 over s minus -1. Okay, now just looking back at our table of Laplace transforms, keeping in mind, right, that the Laplace transform of e to the at is 1 over s minus a. What we're going to now say is, all right, we have 1 over s minus a. Let's convert that to e to the at. If we have a constant times 1 over s is going to be related to that constant, right? Because 1 over s was related to the constant function 1, so we're going to have k times 1, which is just k. All right, now going back to our example, what we want to say is, what is 1 over s related to? Via the Laplace transform, that's related to the constant function 1, so we're going to have 4 times 1 there. What is 1 over s times s plus minus 2 related to? That's related to e to the -2t. The constant 4 is going to come along for the ride, so we're going to have plus 4 times e to the -2t. 1 over s minus a is -1, so we'd have e to the -t here, and the -7 factor is just going to come along for the ride. And via the Laplace transform, what we've called capital Y of s is going to be related to little y of t. Alright, so now that's the inversion step. Okay, so we don't have to use like the L inverse notation if we don't want to, but just note that via the Laplace transform where it's inverse, we can say what the functions of s are related to in terms of functions of t. So now we've finished our problem. We've solved the differential equation. It comes up to 4 plus 4 times e to the -2t minus 7 times e to the -t. So there's our solution. Okay, and keep in mind, what was it a solution to? That solves what initial value problem? It solves this initial value problem, y double prime plus 3y prime plus 2y equaled, in our problem it was 8, and the initial conditions were that y of 0 equals 0 and y prime of 0 is equal 0. So in these two videos we went through the Laplace transform method for solving that initial value problem. I just want to note that that's a second order forced differential equation. We could use our methods from Unit 4 Part 1 using the method of undetermined coefficients to solve that differential equation as well. This is another way to do that. And that's it for this video and this example.